Welcome to our AP Chemistry Chapter 14 notes over chemical kinetics. It is going to be a very different topic than most of what we discuss in the year. It's going to feel different. It's going to have different calculations involved with it. It will fit with the rest of chemistry. However, it just has a very different feel to it. So just letting you know from the beginning, it feels a little different than what we have done and will be doing for the rest of the year. Chemical kinetics studies how fast a chemical reaction occurs, what those factors are. So could we speed it up? Could we slow it down? And even we try with small, simple reactions to determine the mechanism. That is, how does the reactants form the products? So let's look at the rate of reaction. Rates of reaction describe how fast reactants are used up or how fast products are created. And rates of reaction are going to have a concentration term. So check out how we have molarity, moles per liter. There's a concentration. And then we have a time term. And it can be seconds, minutes, hours, days, whatever is appropriate. Most chemical reactions, especially like the ones you did in pre-AP chemistry, you mix the two test tubes and it happens right before your eyes. So we're usually operating on seconds. Slow reactions could be minutes, but there are certainly other ones so slow we could be talking hours, days, months, years. However, whatever time frame is appropriate there. So, getting these measurements of concentration could be tricky. Maybe if we're working with an acid and a base, we could do a titration and do a titration to see the pH right now, and then wait 15 minutes and do it again and see the new pH, and wait another 15 minutes and do it again and see that pH. That, of course, it would be for a very, very, very slow acid-base reaction. Most of them go much faster than that. What is often very helpful, and we will use a lot in this chapter, is a color change. If we have a particular chemical that will give off a color. If it's a reactant, we could time how long it takes that color to disappear. If it's a product, we could time how long it takes color to appear, and we can even use computerized equipment to even do that for us, which makes it very simple on our part. We just get the numbers and then we just analyze the numbers from the equipment and we make our decisions based on how it works from there. Another rather simple possibility is if a gas is given off or used up, we can measure change in pressure. So let's talk about how we're going to express these changes in concentration and over an amount of time. So I have this example equation of dinitrogen pentoxide and nitrogen dioxide forming oxygen gas. And if I'm given the information that this here, the nitrogen dioxide, is forming at this rate, I want to know what's the rate for the other two things in the equation. Now I'm going to start solving for oxygen just to have a place to start. All right, so for oxygen, I'm going to start with what I know, just like we always do. We start with our known information. I'm going to be forming 0.0072 moles per liter per second, and it's very helpful to label this, moles of NO2, because that's what I was told is forming right there in the problem. So now I want to use my mole ratio and say, from the balanced equation, 4 moles of NO2 is going to be worth 1 mole of O2, right here from the coefficients of my balanced equation. So you see I take that number and I divide it by 4. That really is all the math that's involved. Now, did you look at the equation and go, oh, well, if I know this number and I multiply it by 4, I'll get that number? I point that out because that is something very, very common that students want to do. But it's not going to be multiplication. It's going to be division. So I strongly, highly, highly recommend you put it into railroad track and let the railroad track tell you the math. Check out how I'm going to get a moles per liter per second of O2, and all I have to do for the math is this. Okay, so 0.0072 divided by 4 into my calculator tells me 0.0018, and that is molarity per second. which is the same thing as saying a moles per liter per second. Now let's do it for N2O5. I have the same given information, but I have a new mole ratio. 4 moles of N2O, nitrogen dioxide, is going to be 2 moles of dinitrogen pentoxide. Do I need to reduce that fraction? Not really, because I'm going to be using the calculator anyway at this point in time. Yep. And so we see that it's going to be a 0.0036 when I do this math. Now I want to add something to this, and that I'll write it this way, moles per liter per second. Notice how we could write it either way. You need to be familiar and able to handle either way. I'm going to put a negative sign here. First time we've ever done that in a rototrack. Why would I do that? Because we're actually using up this. We are losing it at this rate. We are gaining oxygen at this rate, and we're gaining nitrogen dioxide at that rate. So it's very helpful to have the sign there to let us know what kind of change as well, whether we're gaining it or we're losing it. Okay. Now the last thing I'm asked in this question is, what is the rate of the reaction? That is the overall rate of the reaction. We define the rate of the reaction to be per mole. Not per 2 moles or per 4 moles, but per mole. Well, our oxygen is already per mole, per 1 mole. So for our oxygen, that is also the overall rate. But what about for our nitrogen dioxide? Well, our rate for nitrogen dioxide is 0.0072 moles of nitrogen dioxide per liter per second. And I'm going to, it's right now per 4 moles. So I'm going to divide to get, I'm going to divide to get per mole, per single 1 mole. Okay. So do that math in the calculator, and we get 0.0018 moles per liter per second. All right. So we just divided by the number, the coefficient there, because we wanted a per 1 mole ratio going on there. Okay, what about our N2O5, our dinitrogen pentoxide? Well, we had found for dinitrogen pentoxide a 0.0036 moles per liter per second, but our coefficient there is 2, so we divide that by 2 and we get a negative 0.0018 molarity. Now, do you see what just happened? Our rate for the overall reaction is the same for each of them. So while we would have to do the math to find each one individually, when it comes to finding the overall rate of the reaction, you could pick any one you want, and you would still get the same answer. If you do it correctly, you would get the same answer every time. Now this one is a negative just because we're using that up, but it still tells us what we want to know, and that is that the overall rate is 0.0018 per mole of reaction. So lots of ways we could express this. We expressed it as a per mole of oxygen. We expressed it as a per mole of dinitrogen pentoxide. We already had it as a per mole of nitrogen dioxide, and we can also express it as a per mole of reaction. That is, if every piece of the reaction was in 1 mole, there we go. So please, please, please use a rototrack here to let the math show you how that works out, whether you're multiplying by 4 or dividing by 4, because your gut instinct is going to be, okay, take this number, multiply it by 4, and that is not the way to do that. Please don't do it that way. Trust me, you're less likely to mess up with a rototrack. All right. So maybe math is not your thing, so let's look at a graph. Here's kind of graphically what's going on. We can see how our amount of reactants or reagents, synonyms of each other, the amount that we start with is high. Notice how we start with 0 products. That's typical of chemistry. And as the reactants are used up, the products are formed. And I want to point out, do you see some sort of symmetry between these lines? I hope you do. We should always see symmetry. Now, it's possible that we form twice as much product as we had reactant, and then my line would not be exactly symmetrical, but its curve would still match in terms of a whatever this does, that does times 2. Or maybe I'm using up twice as many reactants to form 1 times as many products, and then so my product line would be the reactants line divided by 2, sort of a thing. So there's many forms this chart can take, but it's showing us the same thing. How fast the reactants are used up, how quickly the products are made, and the slopes should be very, very similar to each other unless you have that multiple in there, and then it's simply a multiple of each other. So expect that. Okay, now just to let you know, what we're attempting to do is find the rate of change at any given time, maybe like that particular point in time. Well, unless you want to start using some calculus, and you could certainly do some calculus, not going to tell you couldn't, but let's not use calculus. Most of us would rather just quickly take some algebra and figure out what is a very, very, very close approximation at that point. So what we're doing is taking what is the change here, dividing by the time there, getting the slope of the asymptote so that we know its point there. And we could do that with the reactants, we could do it with the products. Oh wait, how did I know the red line was for reactants? Well, I know because I started with some amount of them, and I started with like no amount of that. So big hint there. If there's not directly told to you in the equation what you're starting with as well. So all these pieces between the graphs and the equation and the calculations, they should all match up. Expect them to match up. All right, let's talk factors that will affect reaction rates. And we're not going to get into all 4 today, but there are 4 general things that can speed up or slow down a reaction, and that is catalyst temperature, the nature of the reactants, and the concentrations. We're going to talk today about the effect of catalysts on this rate. So we solved for rates. What would a catalyst do to that rate? Well, it depends on the type of catalyst. There's 2 catalysts. You probably need to know just a general idea in your head about what makes each catalyst different. There's a catalyst that can lower the activation energy. That's one option, by forming what we call an intermediate, and we'll get to that thought. And then there's catalysts that are called surface catalysts that literally just are a surface. But they're a surface that the reactants are very likely to stick to and therefore be able to find each other on. Because if the chemicals don't come close to each other, there's no way there's going to be a reaction. So let's consider this reaction here. 2 ceriums and 1 thallium will form 2 ceriums and 1 thallium. And I start off by saying this is a redox reaction. Can you prove this is a redox reaction? You better be able to still prove, this is your review, prove this is a redox reaction. Cerium's going from +4 to +3, that would be reduction. Thallium's going from a +1 to +3, that would be oxidation. You hopefully still have that skill. You all exercised it well during electrochem. Be sure you don't forget that. Okay, so let's ask ourselves some questions. What would it take for this reaction to occur as it is written? In other words, what would need to collide? We'll check out how I have 3 reactants. Do you see 3 reactants? 2 ceriums and 1 thallium. So I would need to have 3 atoms collide at the same time, plus I would need to have 2 of those 3 be cerium and 1 of those 3 be thallium. So I have a 3-particle collision, and I would need a thallium and 2 ceriums. Then, once they do collide, what would I need to have happen? Well, we've done some redox, and so we should have some movement of electrons. We should have thallium losing electrons to cerium. So not only do I need 3 things colliding all at once, I would need to, at that same time, be able to transfer electrons. Does that sound like a hard thing to have happen? Because that could be a hard thing to have happen. The statistical chances of three things hitting together all at the exact same time and hitting just right so that two electrons are moved from thallium, one to each cerium, that could be asking an awful lot of the situation. So it turns out if we add manganese 2 ions, it increases the rate of the reaction. It is thought it works this way. A cerium finds a manganese and transfers some electrons from manganese to cerium. You better be able to prove how that worked. Know your oxidation and reduction numbers. And then that process of a new cerium, check this out, a new cerium reacts with that already used manganese and grabs some more electrons as well. And then that doubly used manganese is going to collide with thallium, and those two electrons from thallium are going to go back to manganese. Now overall, when I add up all these equations, very much so like a Hess's law idea. I see an Mn plus 2 over there, and an Mn2 plus there, and I see an Mn3 plus there, and a 3 plus there, and a 4 plus. So when I add this all up, I get that overall equation. Which brings us to the point of, if we're using a catalyst, it should not be something that appears in your overall equation. That's one of our definitions of a catalyst. Okay. So, how is our manganese ion involved? Let's call it an intermediate. It goes in between the ceriums and the thalliums. It does some of the work for us. It does a trade, and then another trade. So we'll call that an intermediate. The manganese ion is involved as an intermediate. Okay, how can it be involved and not yet consumed? Okay, well, we started with manganese 2 plus, and we ended with manganese 2 plus. So that's the not consumed part. Okay, now notice this is different than it forming an Mn3 plus and an Mn3 plus. That's an intermediate. Mn4 plus and Mn4 plus, that's an intermediate. But a catalyst is seen when we start and end with exactly the same thing, and the extra pieces cancel. All right. Why is this easier than before? Now here's the big question. Why would this speed up the reaction? How many things need to collide in this first reaction? Please tell me 2. How many things need to collide in the second reaction? Please tell me 2. How many need to collide in the third reaction? You get it again? 2. What's easier? 2 things colliding and transferring electrons, or 3 things colliding? Now notice, it doesn't matter that we're doing it in more steps. That has nothing to do with it. All right. What we're looking at is how many particles need to collide to make the reaction happen. So why is this easier? Because we need less particles colliding, literally. That's why it's easier. Yeah, it does it in more steps, but that's fine. Statistically, there's a much greater chance of 2 particles colliding than 3. Okay, what if we drew it in our energy diagram? We saw this energy diagram earlier as we were talking thermodynamics, and we had even this thing marked activation energy. What is activation energy? That's the energy needed to have the reaction occur. So without the catalyst, we follow the blue line, and it takes this much energy. Notice how high that hill is. Okay, it takes that much energy for 3 particles to collide and transfer electrons at exactly the right time. Now with manganese, overall, it only takes this much energy. Is that going to make the reaction faster? Well, yeah, it takes less energy, so it's more likely to happen because you need less energy to get it started. Okay, so this is a lot like striking a match. I need to put in, if the match lit on fire in the box, I'd be in trouble. I want some amount of energy that I have to do to strike it, but then once it's struck, I want to be sure it burns. So I'm wanting, that energy out. Okay, so with a catalyst, less energy to get started, but notice same amount of energy out in total between where we start and where we end. The catalyst would never change those points. It just changes the size of this hill. Speaking of the hill, often this method, and especially with this diagram, having a catalyst is often called a tunneling effect. Why would we call it a tunneling effect? Well, if we do refer to the blue line as the original hill, you can see how we've made a tunnel through the hill. It takes less energy to get through the hill if we follow the tunnel. Another vocabulary we use for this is alternative pathway. So now the reaction can decide, is it going to go through this path or is it going to go through this path? So now we have an alternate. So that is the type of vocabulary often associated with catalysts, is it provides a tunneling effect or an alternative pathway. Okay, why does the activation energy decrease with the catalyst? Well, to give you specific reasons would be beyond the course. Very complex. However, what is the simple answer? Without the catalyst, you need 3 particles colliding. And the sum of all their energies has to be just right to get those electrons to transfer. With the catalyst, we only need 2 particles colliding each time, and so we need less energy. It's more likely that we'll have 2 particles collide with the exact amount of energy needed than we are 3. So it does lower the activation energy overall, just as a whole, by having only 2 particles needed. Okay, so that was the type of catalyst involved in the reaction. Notice it does not appear in the overall equation, and you end up with it as a product and you start with it as a reactant. Okay, that's going to be very, very, very necessary to keep clear in your head when we get later on and talk about intermediates again. So be careful about that. The second type of catalyst we call a surface catalyst. Okay, now a surface catalyst is just what it sounds like, some sort of surface, and some things that are otherwise floating around want to stick to that surface. Typically, this is between gas and a solid. So we would call this a heterogeneous catalyst because the form, the state of matter of the catalyst is different, hence hetero, different than the form of the reactants that we're seeking to attract to the surface. Whereas earlier we had manganese ions in a solution of cerium and thallium ions, and so being all the same, we could call that a homogeneous catalyst. This vocabulary is not often seen on the test, but in case it shows up in the textbook or other stuff you are looking at, I want just you to understand what they're referring to. It really makes very little difference to how you treat it. What does matter is your understanding of how it functions. So let's do an example. Okay, you've got enzymes in your body, and they work as catalysts. So I eat some sucrose. Yum, yum, love my sucrose. And if I waited for that sucrose bond to break naturally in my body, I'd be waiting a long time. But we go into the body and we have an enzyme. And an enzyme will have a particular pocket that fits into, and the enzyme will break the bond and then reject the fructose and glucose. And in the process, there's some energy change. I'm like, ooh, I feel all sorts of sugar high. And then the enzyme, notice how the enzyme's not changed. It can just keep cycling through and doing more. If it weren't for enzymes, enzymes are a natural catalyst in our body. If it weren't for enzymes, we would all have the metabolisms like a tortoise. Now, on the other hand, we might all live like 500 years, but is there really a difference between moving slow and living 500 years and moving fast and living 100? I don't know that. It'd be a philosophical argument, which is better anyway. What we do with this in a very practical sense is we use it in the catalytic converter of your automobile. Okay, we really do not like carbon monoxide coming out of your tailpipe in your car or truck or van or whatever you're driving. Carbon monoxide is poisonous and it's very difficult to get out of the body. Yes, carbon dioxide is poisonous, but your body can get rid of it a lot easier because your body makes it, and so it's used to getting rid of it. right? So let's say your car accidentally, the engine in its combustion process makes some carbon monoxide instead of carbon dioxide. As that gas is exhausted, it goes through the catalytic converter, which is closer to the engine of your tailpipe. It's not the muffler part on the very end, it's closer up. Okay, the carbon dioxide finds this surface inside the catalytic converter that it wants to stick to, so it does. And then the next time some random oxygen that hasn't reacted floats by, it also wants to stick. And the particular chemicals that your catalyst bed is made out of makes it very easy for oxygen, which we know is diatomic, to split up into individual oxygen atoms. And when split up, carbon can say, hey, how are you doing, Mr. Oxygen? You with anyone today? No, you're not with anyone? Okay, why don't you come on over? Okay, well, they don't have that conversation. But we certainly have a difference in electronegativities going on here, and the opposites attract, and we form carbon dioxide, which would then float up off the catalytic bed and into the air with all the other gases through your tailpipe. Meanwhile, we have another oxygen waiting for another carbon monoxide to come around. So, one oxygen can do double duty, and that's really cool that it helps ensure that we get nothing but carbon dioxide coming out of your tailpipe. We really don't want carbon monoxide. They're both greenhouse gases. They both would suffocate you because you need oxygen, not carbon monoxide or carbon dioxide. But if carbon monoxide gets into your lungs, it sticks there very well. It takes a long time for your lungs to naturally get it out of your system. So it is certainly a health hazard, if not environmental hazard. And so that's why we pay about $100 to have a catalytic converter. Okay, so we're going to stop there. That's the basics of kinetics. That's the basics of talking about rates of reaction, typically expressed in concentration and time, molarity per second or moles per liter per second or per minute or per hour, whatever, and the effect of catalysts. Okay, so you will need to be able to describe how a catalyst is working. Is it a surface catalyst? Is it involved in the reaction? And you'll need to describe what would it do to that energy diagram, and you would need to describe things such as, can you prove that it is a catalyst in that it appears as a reactant in the first equation, it's then a product in the last equation, it's unchanged between those two, and it does not appear in the overall equation. All right, so lots more of kinetics to go through, but we're going to stop here and be sure that you can master what we've already discussed. Good luck.